Good. So let's go ahead, and today we're gonna talk about linear regression, or least squares method. You have seen it several times. So linear regression. And to start with, I have here the picture that we have seen in the last lecture. In the last lecture, we were dealing with the problem of what if I did a couple of experiments, 1,000. I measured 1,000 data points, and now I assume that all these data points are just a measurement of one constant value of some quantity. But the problem is that I just have some measurement noise in the data. And what we did basically, well, we found out that arithmetic mean is the best estimator to get closer and closer as the number of measurements increases to the true value, to the one. Basically, what in some other perspective, what we did, and I hope my drawing will be good here. Ah, nice, almost. Basically, what we did based on this data, we tried to get a histogram in some form and actually fit a distribution. Fit a normal Gaussian distribution to this. So, okay, well, it's just my bad drawing, but if the distribution looks like this, the distribution only has these two parameters, mean and the standard deviation. So, for example, here we would estimate that this value of this constant is slightly below its true value, and we would even reflect the uncertainty that we have, because our measurements are telling us each time something else. Today the picture will change just slightly. Let me do the same color code if I can find maybe this is blue. So today the setup is almost same. We performed couple of experiments. Maybe this time we would know some difference between these experiments, which we would quantify in the variable x. Practical example, which you will also see in your exercises. We will take a couple of measurements with different temperatures, some gas, and we will observe what are the pressures. How would the pressure change? So for let's say temperatures, some independent variable x, we do a couple of measurements, and we record the corresponding responses. Let's just call them y. And if we just now compare these two pictures, well, if we just take this one and we somehow rotate it and tilt it, well, we can immediately see that now our task might be really similar. Let's say we are trying to find again some mean value, but just this time this mean value will be a curve that will depend on this independent variable. Yeah. And as I draw this Gaussian distribution, well, we will again take all all the possible measurements, and well, now this is quite tricky to visualize, but we can draw again some sort of a mini Gaussian distribution that would go along this line, and will be again like the histogram here. We will take each of the measurements into account, and we will try to find the maximum likelihood estimate, and we already know that this maximum likelihood estimate is the same as least squares estimation. So far so good? Doesn't maybe remind you of anything familiar, but it will in a second. How can we encode this? So let's say that we have some Kate observation, and our Kate observation might be, we had something similar in the case of estimation of the constant. So we can explain each observation, each data point with some model, with some prediction, and the rest is the uncertainty. So some measurement noise. And we talk about the linear regression. So let's put it this way. So our model, our prediction will be, let's have it as simple as possible, just a line that will be parameterized by two values. So the slope of this CN line, and the abscissa, intercept, offset, or bias. Yeah, just to, this is like a abscissa. There is maybe double S, or intercept, offset, or bias. Yeah, those are the names for this B, which is actually, well, if our slope is 0, then this would boil down to the estimation of the constant that we saw last time. Okay, of course our assumptions will remain as in the last week, that the error, so each time we are measuring, so if there was no error, we would be measuring points on this CN line. Since there is some error, it will add, and this error will be Gaussian distributed, and to be, or normally distributed, to be really nice. Well, we have some zero mean. So let's say our sensor is good in average. On average, it gives us the true value of what we try to measure, and well, we have some estimation noise, some standard deviation of this noise. Before we do some mathematics, which you will all know, did you ever wonder why do we call it regression? Also in Slovak we say regresia. Regression means something. What does it mean? Yeah, exactly. It means some deterioration. Something is going wrong. Yeah. So why is it that we call it regression? It's just like we inherited it somehow from the past. Mr. I guess the name is Galton. No, Mr. Galton was doing. He was a biologist, something like that. And he was doing this sort of experiment. He took two groups, parents and children, and he measured the height. So he was then constructing this sort of a graph, like height of a parent, and then the height of a child, of course probably some grown-up. And if you are about to do some prediction, what would you expect? What is the correlation? The tall parents have what? Tall children or small children, or
Usually tall.
yeah, exactly. And the small parents or short parents would have small children. So you would expect to see something like y is equal to x sort of curve. But Mr. Galton found something like this. It was the real data. If when he plotted them, he found there is some deviation. He found out that okay, if we have tall parents, then their children are slightly shorter, and if we have small parents, then their children are slightly taller than expected. And he concluded that okay, the height of the people of the population is turning towards the mean, and what he said, like this, the height of the children is regressing, so descending, as Jakub said, regressing towards the mean. Towards the mean or towards the average. Yeah, and just because he used this word regress, then that's why we use linear regression. That was for the fun historical facts. Let's do some math. So, of course, if we now take our data points. What are our data points? Let's start with this simple example that we always have some tuple, some pair of the. In the kth experiment, we had this temperature and we measured this pressure. So we have some independent and dependent variable. This is repeating from similarly as we did last time. So let's say we have capital N number of measurements, and this K is our iterator. So our task is, of course, to find what are the values of A and B. We know we can pose this as an optimization problem. It's a standard least squares. So let's do it. For some very good reasons, we will put this 1/2 in the as a multiplier of our objective function. And what can we do now? Well, we take a sum of squares of the deviations of what? Of our data points from the mean that we are trying to find, or in other words, we can already plug in what we have assumed here to be our model. So minus AXK minus BK. Good. So how do we find A and B? What are your suggestions?
We derive.
We differentiate. Differentiate this objective function with respect to x is given, x are numbers. A and b, exactly. Yeah. So we want that this this function differentiated with respect to a is 0, and with respect to b. So let's do the part with respect to a. What do we get? Okay, maybe I'll just start. Okay, we have a constant of 1/2, so let's just keep this constant here. We have a summation, so derivative of a sum is a sum of the derivatives, so the sum is staying with us. And then we have a quadratic function.
We can multiply the brackets within itself. Simplify.
Why cannot we just say, like, what is the derivative of anything to the power of 2? Yeah, so 2 times this bracket, yeah. And what we are missing, the derivative of the interior of this bracket, right? Which is
xk minus xk.
Minus xk, exactly. Okay. So let's continue and let's do the derivative with respect to b. That might be even simpler. So nothing will change until this point, right? It's the same expression. 1/2 sum of k from 1 to n, 2 times yk minus a xk minus b, and then derivative of the b will be -1, exactly. Okay, so let's somehow start to work with this.
We can cancel the number 2 and 1/2.
Exactly. 2 doesn't depend on the k, so these guys are gone. We can also cancel this one. What do you say? Yeah.
And just
It's just the constant. Yes. So let's then start working on, if this is equation 1, this is equation 2. Let's maybe take equation 2 first. Looks slightly simpler. So we have 0 is equal to. Now what do we have here? We have the sum of yk, sum of these guys, sum of these guys. Yeah, so we can break this bracket into individual sums. Good. Yeah, so this will be just the first sum. Yeah, sum of yk's. With the second sum, I see there is a minus, and there is also this common factor, common parameter a. So we can factor it out in front of the sum, and with the last guy, we have seen it here already several times. We can do another trick, which will involve the fact that we do not have to write the sum again. How will it look like? right? Everybody sees why this is n times b, right? I'm summing minus b again, minus b again, minus n times b. Okay. Can we already find out, so what will be our estimate of the b? It's almost separated from our expression. Oh, let's do that. This is n. Yes. So let's do that. What do we get? We just take the minus mb to the left hand side, and we divide by n. So we get, let's do it in this way. 1 over n with the first sum. And then we get minus a times 1 over n. I don't put them together, just you will see in a second why. Of xk. Oh, makes sense. Good, so if I know my data y, I know my data x, I can already calculate here something. I still don't know the value of a, but at least I have this relation. And
may I ask, why do we have that 1 divided by a to start?
Again, 1 over n?
Yeah. Oh, that's n. Yeah.
Yes.
Oh.
It's a? A to you? Okay, thanks. Yeah. Tell me. Let me know if this is unreadable. I'm happy. Now you will say this. It looks like some other letter. Okay. But let's see these expressions. What are they? Solved. What are these expressions? How can we write it, or what they are? I sum several numbers, n of them, and I divide them by the number of the summends, by the number of the guys I have. There are arithmetic means, right? The arithmetic mean, it's all over the place. Once you see it, you cannot unsee it. So we can even say, okay, this offset bias abscissa intercept is relatively simple. Well, I just take my data, x and y, I calculate their means, and I have this nice and neat relationship. Good. It might turn out that this will be similar for our parameter a. Let's see. Let's try. Let's try to see whether we get something similar. So the only complication and the difference from the previous equation is that everything here is multiplied by xk. Of course, to make it easier, we can just cancel this minus. The same thing as we did with the minus 1 here. And let's then try to rewrite this. So need to get 0 being equal to what?
No, we want to solve it for a.
Yes.
So can we just let the entire bracket disappear, because there's multiplication between those two brackets, and either one or the other is 0.
One or the other is 0?
Yeah. So because it's equal to 0.
But there is a sum. I'm not sure. Well, I mean, we have n of these multiplications. I'm not sure whether it will whether this will happen. But actually, we will not solve for a. We will just make it into some convenient form, and then we will see how we can solve it easily. So let's just get it into some convenient form, and the convenient form will be just that we do the multiplication between these two terms. So we definitely have sum of yk times xk minus the a will be again factored out, so we have minus a sum from k equal to 1 until n of xk squared, and the last term will be minus b times sum of xk until n. This is everything with what that we will do with this. There is no immediate mean, but of course we can do like we will divide the whole equation with n. We will see again some arithmetic averages would appear. But let's observe something else with the expression 2 with the expression 1. The structure is kind of similar. We always have some actually constant, yeah, because if we which we know these data, we can calculate these sums. Then we have minus a times there is of course another sum, another coefficient, we might say, so something which we can easily calculate from the data, and the same goes for these last expressions. So where I'm heading to is, what if we just put this into the form of NP is equal to, I don't know, some nice letter n, which is just ax is equal to b, but I don't want to use the ax is equal to b because there are already some a's and x's. So what if we just turn this expression into the form of linear algebraic equations? Well, and then we know what to do in MATLAB. We just write m/n, and we are done. We have our variables p. Yeah. So now comes the intellectual stimulation. If I say that our vector p is of course the parameters a and b, how can we write this down? What will land where? How will the matrix M look like? How will this vector n look like? What do you say? How would you start thinking about this?
First term is the last matrix.
This one? Or
The sum is the first term.
this one? No. Tell me, up, left, right, or hotter, colder.
We're doing the first equation, right?
For example, yes.
Or both?
Well, I mean, we will represent both of them in the matrix form, right?
I mean that the first term of the first equation.
This is first equation, right?
Yes.
Okay. First term is 0.
On the right side.
Okay. First term, yeah. This sum.
Yeah. There is no a or b, so it is on there.
Exactly. Yeah. So we can also turn it very easily in our head. There are always minus signs. So let's pretend that they will go to the left hand side. So what we are left with is this term. So sum of yk xk from k equal to 1 until n. Then we can either continue here or just construct the first row of the matrix. What comes where?
The first place isn't the second underline thing in the equation. Yeah.
Sure. So we have sum of x squared. What is left? It's not that hard to find out. Yeah, it's sum of xk's. Yeah. Right. So we express this first equation: a times x sum of x squared. We have it here plus b times sum of x will be equal. So we'll have a different sign than the sum of yk times xk. Good. And now the easier one. We started with the more complicated. So the easier one will be, how will it go?
The second equation. It should be again like the first part is on the left side. So or on the right side in the matrix equation.
Yes. Exactly. Sum of yk.
And then the first element is sum of xk.
Sum of xk.
And the last one is n.
And the last one is n. I mean, this one seems to be like the odd one out, but again, whenever we want, we can also transform it into what is n. Well, it's the sum of ones which goes from k equal to 1 until n. Yeah. So if we just want to see also the sum, because we have sums everywhere. Yeah. Okay. Well, it's now quite easy. All what this matrix contains is our data, either x or, well, this is only x, and here we have on the right hand side we have a mixture of y's and x's. So our MATLAB routine will be very easy. We just do this inversion of matrix A times the vector n, or we solve this system of linear equations. Easy peasy. What? Again?
Isn't x squared from 1?
Why? It's just 5. Is 5 squared a problem? Yeah, good. Thanks. Very good question. Yeah. So this is just data. in some form. Where we are heading to is well, if we now have more parameters, these matrices would grow, and we will get more sums. So we should head and try to make use of the matrix vector notation to simplify this. Yeah, I already wrote only a few sums today, and my hand is already tired of writing the sums. One particular thing that that we should before that touch upon is the notion of making the data centered or normalized. Centered or normalized data. So let's imagine our very same problem. Let's say our y hat is equal to let's write it simple, let's write the y. Our y is equal to ax plus b. What we already know, well, we already know our best estimate for the b, which involve these means. So we already know that our b is can be nicely expressed as a times x bar minus plus. Makes sense. Okay. There is minus, right? We have wrong sign here. Sorry about that. Nothing changes in our narrative. I just realized it now that somehow the units do not agree. So let's write it again. The mean of the y's minus a times mean of x's. Okay, so let's plug this in and see what we get. So a times x plus y bar minus ax bar. Okay. It seems that we can make friends of the terms with y and the terms with x. So let's just put the y bar on the left hand side. And factor out a, right? Makes sense. But what does this mean? Because we have the knowledge of what our bias offset would look like, we can actually quite easily forget about it. And what if we just in the very beginning transformed our data, like we will have, let's say, like some y tilde, let's call it subscript c, and x tilde subscript c. So we will take our measurements and subtract their mean from them. We will do the same with our independent variables, and this already means that we centered which spelling to use, that we have that we centered our data. That our data have what? Let's do some example. Let's say our x or y, doesn't matter, is 5, 4, 3, 2, 1. Yeah, so like the separate values. What is the mean of x? So now if we do x centered, x minus x bar, too much, x minus x bar or x minus 3, what do we get? How will this second row read? And I don't know why did I write it in the descending form, like 5, 4, 3, 2, 1. I should have gone 1, 2, 3, 4, 5, but
2, 0, minus 1,
minus 2. What does it mean that it is centered? Well, we basically removed the mean from the mean value. So now we shifted if our data x and y would look like this. Oops, sorry. And we have the mean of x here, and of course the mean of y here. Well, then in our centered coordinates, we'll get, well, the data would look the same, but there will be 0 here and 0 here. Basically, we take this cloud of points and we shift it somewhere such that in the center we have the origin. We have the origin. We will see why this transformation is beneficial. Of course, because now it's easy. We already talked about it somehow in the first lecture. Now we can directly see, okay, is there positive or negative correlation? Should I expect my slope to be positive or negative? So if we now just take whatever value of x, let's say we took a positive one, if we find the corresponding pair which is positive, that would already indicate our correlation is positive. Also, if we took the negative value of x, we get negative value of y. Yeah, it's just very simple tricks, very simple things to see. Yeah, imagine you have here the temperature in the kelvins, yeah, from, I don't know, 250 to 350, and here you have a pressure in the bars or pascals. It's not that easy to see what is the. Of course, we can plot, but with more data, it's much harder. So it's not that easy to see. What can also happen? What can also help us is to do another small transformation. Another small transformation will be, well, let's take our centered data, x minus, okay, and let's now not only use the means of these variables, but we can also calculate the standard deviations. Yeah, we already know how to do that. And okay, so let's just expand slightly left-hand side and the right-hand side with the standard deviation of y divided by standard deviation of y. Yeah, we did nothing bad to the equation. We just multiplied it with 1 in some form, and let's do the same on the right hand side with the standard deviation of x.
What's the first part of y?
This one, sigma y divided by sigma y. So it's standard deviation of y, standard deviation of y. In case, so standard deviation of y would be what? Will be the square root 1 divided by n minus 1. Yeah, that was the Bessel correction, and we get sum of yk minus y bar. Yeah. Same for x. Yeah, just replace with the x's. So how far the values of y are spreading from their mean. Okay, and let's then do some kind of a shuffling. We keep the sigma y's as the numerator denominators of the left hand side here and of this bracket here with the sigma x, and we divide by 1 sigma y and divide by sigma x. So if we do this, 1 minus y bar divided by sigma y is equal to, there will be definitely a, there will be x minus x bar divided by sigma x, x. Good. This is what we want for some reason, and what do we have left? What do we have left? So sigma y we divided by, so we need to have the sigma y in the denominator, and there will be some yx. Okay, we didn't need to divide by sigma x. It just stays here. Yeah, that was. So we just do 1 over sigma y. The question is, why did we write it in this form? The answer is what we are doing by dividing this centered variable with its standard deviation. We are actually making whatever standard deviation this variable had, we are making this new variable, which will have, let's call it yn, and this variable will have, well, zero mean. We already know it because we are centering. Yeah, we are removing the mean, but also this division would cause that we have a standard deviation of 1, and this is the way how the same will go, of course for this variable. So now we actually can start to even compare the variables between itself. Yeah, imagine this, and you will see it in your exercises. This is the pressure which I measured. The pressure goes, I don't know, from 1 bar to 10 bars, or we just express it in pascals. Yeah, so we have 10 to the power of 5, 10 to the power of 6. That's quite a large spread. And now we compare it with some temperature in the kelvins. Yeah, the spread might be just 100 kelvins or 100 degrees. So it's hard to compare, hard to actually make sense of the coefficient of this slope that we get. with this transformation, we will start to, so let's say we have this coefficient, let's call it an, like the a, the slope which relates these normalized variables. This coefficient will turn out to be somewhere in order of -1 and 1. Yeah. So even in the situations where we will get more and more independent variables, we can very easily start to compare the strength of the correlations. Yeah. If this coefficient is closer in absolute value to 1, it means that our measured variable really heavily depends on that particular independent variable. You will see it in your exercises very soon. Yeah. So then this is the way how we normalize the data. Let me just write it. Normalize data. If I talk to other teachers at this university, in this town, in this country, in Europe, in the world, we all agree that just to do the normalization, whatever task you are doing, it does not have to be identification, doesn't have to be regression, can be just control. Just to do the normalization saves a ton of time and ton of nerves, ton of torn hairs. So normalization is a key to make the data reasonably shaped. We use normalization or standardization in the exercises.
I guess
Standardization is a more common term. So if you say normalization, it's not clear what you mean. If the normalization makes the variables to have zero mean and standard deviation of 1, then we talk about the standardized data. Yeah. Maybe just to recall. How do I go back? Maybe just to recall, this is something similar that we have seen last week. Yeah, just look here at our expression when we were trying to derive at the very end the confidence interval. We actually did the standardization of the estimation error, because our statistics chi-squared works with the standardized variables. So whatever we estimate for our standard deviation of the estimation error, we just correct it. We just standardize it. Good. Did I say everything? So maybe for your exercises, you will also try to derive some confidence intervals. Let's just do it in the simple fashion. let's go back. Where was our lecture from last time? So where did we ended up last time? Last time we were trying to estimate a value of some constant. What we found was this estimate y bar hat, and by subtracting some particular number from it, adding some particular number from it, we actually found out, well, with this and this percent probability, this and this percent, so with alpha percent probability, in this interval, oops. So it's right hand side, it's left hand side, my true value y bar, well, it will lie somewhere there. Yeah, so our estimate tells us 0.95 to 1.12. Well, so the true value of 1 lies within this interval. And what we only need for this is to have a couple of ingredients. We need the estimate of this constant. We need we need the standard deviation of how this estimate is far from the measurements, and we divide by the square root of the number of measurements, and this is some standard statistical function that we use. Well, the story is just the same here. If we have and let's just now talk only about this form that we are trying to estimate the slope to make it easy. So we have a estimate of A. Let's say we just did this, where was it? M over n, we just solved this set of linear algebraic equations. What do we need to have now? We subtract some standard deviation, divide by the square root. What was there else? The square root of the chi-square quantile of the chi-square distribution. And we would say that the true value of this slope lies in this interval. Chi-squared inverse. And how to estimate this this standard deviation? Well, if there was not enough square roots, here is another one, and this is the square root of the sum of the deviations of our data with respect to our model, right? We we do the regression. We calculate the predictions of our model. Now we can compare it with our data. We find how our model is basically fitting our data. You will know this also as RMSE, root mean squared error. And we can use it and plug it in, take into account how many measurements we did. We can say what is our confidence in the value of the slope that we achieved. So this is also known as root mean squared error. If you open any paper on statistics, machine learning, when they are trying to predict something, so they are building a model to predict some data, you will definitely come across the RMSE. Sometimes they have just MSE, so the mean squared error. This should be -1, for example. MSE, but RMSE is somehow more practical because what? The standard deviation lives in the same world as our data point. So we can say, okay, our model is now off by, what are we estimating? Let's say we are estimating the pressure, so our model is off by 0.01 bar. Yeah, so that's how our predictions might be wrong. Okay, again, this was the heavy statistical part of this lecture, and let's now go and try to simplify these expressions with the sums and everything, because you know there will come time when we not only have let's say one vector of the data like we measured in the first experiment, second experiment, and the nth experiment. We might start to see situations. Okay, we not only measure temperature, we also measure concentration, and we can maybe even use a square of the temperature. I'm using square. Michaela would already ask, since we have square there, wouldn't this be a problem? Yeah. If I want, I can build a model. Let's put it in this way. A3 some temperature squared, and this still will be a linear model, because it will be linear in the parameters. So the model linear in parameters, we can again use linear regression. Everything will work. But then doing the squares of sums of t's, sums of c's, sums of t squared, and sums of t times y, what were our data, the sums of c times y, it's going to very easily turn out to be impractical to always keep these sums. So let's just say, okay, our data will come, let's say, in this form. We have temperature at the first measurement, at the second measurement, at the nth measurement, concentration first, second experiment, nth experiment, and so on. And maybe we even have these squares or whatever functions that we might like to add into our model. Well, what we see in this structure. So we still have columns which will represent like each particular variable, or maybe its transformation. So we can say, okay, these are still all, each of these columns is just the one instance, is just one independent variable. And well, how many of these variables in general there will be? Well, we just, if we constructed this model, we just have one parameter, second parameter, third parameter, because we had three independent variables. So actually for each column, each variable or its transformation, we will try to find one parameter. So if let's say number or letter P will tell us how many of these independent variables we are taking into account, right? And so if we just transform this example into some more general format, well, we will have the first variable measured at first experiment, first variable measured at second experiment, first variable measured at end experiment. Yeah, so we can combine this structure of having n rows, where each rows represent an experiment, a measurement, with the fact that we have now a couple of these independent variables. No? I see pain in Jakub's face. A lot of pain. I can, at least at this point, I can only promise you that at the end it will be very easy. It just sounds very hard in the beginning. So just bear with me. Let's just write this for the second variable. Yeah. So we have. So if this was temperature, so temperature in first experiment, temperature in second experiment, third, fourth, fifth, and so on, until the nth experiment. Then we have concentration in the first experiment, concentration in second experiment, and so on, until the nth experiment. And what we get here last is the pth value, or the pth variable p in the first experiment, variable p in second experiment, variable p in the nth experiment. And what we get by this? Well, we basically get the matrix. We will call it capital X. So just to see whether you are completely gone for good for today. What are the dimensions of this matrix? Number of rows, number of columns.
P times n.
And again?
P times n.
Almost.
N times P.
Yeah. First row, second row. Am I writing it in a wrong order, like you are used to? Okay. Okay. For the next lecture, we will do it in the other order, but we will. Once we establish this capital X, we will use it a lot, so we won't need to care about the exact number, exact order of what is the row and what is the column. Yeah. I give you that. Yeah. The reason why I'm writing it in this reverse order is that I care more about this column coming from the first variable. Yeah, that's more important than particular number of experiments. We will very easily find examples. Rust, you can tell you about many examples that we have maybe 200 variables, and well, the number of columns is, let's say, 16,000. Yeah, because those are like the 15-minute measurements from 1 year. Yeah, something like that. So then the columns are more important because they are telling about the behavior of particular temperature, pressure, about the particular distillation column, reactor, and stuff like that. Okay, so if we now have this now establish this this notation, so what is our notation to recall? If we are talking about the lowercase x, it is our good old data vector. So just one variable. Yeah. So it's like making this matrix thinner, like removing all the columns, all the p-1 columns. So we are just left with one column. Then if it's, I need to establish how I write capital X and the lowercase x. Yeah, lowercase x, capital X. Yeah, so that's our good old matrix here. What is quite nice that well, let's just assume that our vector of the output variables will remain to be just a vector, which means we will just measure one quantity, pressure, the composition of a distillate from a distillation column, concentration of some products. So with this, let's just do the slight practice with the vectors and matrices. Maybe just the vectors. What if I write expression like this, and this is now the lowercase x? What will this be equal to? So it's scalar product, yeah, skalárny súčin. Let's just first rewrite it. What does this strange looking t means? What should I do with the vector x? Yeah. So yeah, that's what does it mean? So you can also do the pantomime.
You change the columns to the rows.
Mm-hmm. So I have this x1, x2, xn, and I multiply by x1, x2 until xn. What will I get?
Isn't just the sum?
Mm-hmm. x1 squared plus x2 squared plus. Okay. So it's a sum. So can we express it as a sum? Well, where the numbers which are changing here, let's call them k's for some unknown reason. Oh, sorry. And how we can express this as a sum?
this k squared.
Mm-hmm. Okay. Where have we seen sum of xk squared today? It's this guy here, right? How about we now transform all this the whole of this matrix into this kind of neat vector form, because, well, you would agree that instead of sum from k equal to 1 until n of xk squared, it's quite neat to just write x dx, x transpose x, right? So what would be your guess for, or no, let's just do the easy one. So how can we then transform this yk xk, the sum of yk xk? If we already seen this one,
We transpose one of them.
again,
We transpose one of them. For example, the y. And then we multiply it by x.
y transpose x. Would that work? Right, it will be the same thing as let's say writing y1 here, y2 here, yn here, and this will of course give us y1 x1 plus y2 x2 and so on until n. Okay, what was our, so we already know what to do with this one, what to do with this one. Now what about these guys here? I have a sum of just x. How can I represent, what can I do with the vector x or vector y, but let's just start with vector x and it will be same for y. So I represent this sum and I want to use x here as a vector. Yeah, just do x is a vector, so x1 plus, so this sum is x1 plus x2 plus and so on until xn. Że? Yeah, there is 1, 1, 1. So if these y's are the ones, yeah, we just take so let's do this sort of a 1, so that it will have this kind of support, such that we know that this is the not matrix, even vector of ones. Yeah, the one with this leg is just 1, 1, 1 until the same number of elements as the x. Oh, okay. So we can just very easily now rewrite. Let me take this. Can I do the copy here? If I can do the copy, that will be nice. Copy. Paste. Oh, I'm learning something every day. Yeah. So with this knowledge, we can already easily rewrite. So what was it? Xk squared, sum of them. So sum of squares of x was this guy, yeah, the x transpose x. Sum of the xk's is this one here. Sum of xk's in the second row of this matrix, it's just here. Where we can keep just the capital N. It's capital N, not A. A times B. What do we get here in the instead of sum of yk xk? Y transpose x. And for the sum of y's, we just have this one vector of ones times y. So we already simplified the calculations of the parameter A and parameter B, which was just a slope with respect to one independent variable and this bias. A natural question would be, well, if we can somehow find a model. No, this shouldn't have been tilde. Sorry. Our model, let's say in this form. We take our matrix X. Remember, you concluded that this matrix X has n elements, and its number of columns was the same as the number of variables we were doing regression with. It actually has even a special name. It's called a regressor matrix. Well, the P is of course the vector of parameters that we are trying to find out. P of P. And basically this y hat, well, what it is, what will be the dimension of this y hat? So this is P times 1. N times 1, yeah. I think Michaela was saying that, but completely silent. N times 1, yeah. So for each of the experiments, it is giving us the prediction. So of course it's the same size as our measured data, which means we can now say, let's pose finding the parameters P, again as an optimization problem, least squares problem, and what can we do? So minimization 1/2. That's what we started with. Yeah. So what can we do now to represent this sum of squares of differences using our new vector notation? We don't want to write the sum, so if we didn't want to write the sum, let me get there. Well, if we didn't want to write the sum, we just took the vector and transposed it. So now I don't want to write the sum of yk minus yk hat times yk minus yk hat. Yeah, this is a no-go. So what can I do?
Yk was already replaced by 1 transposed times
Yeah, but we want the multiplication. Yeah, so we have one vector, we have a second vector, or let's say we have one multiplier, second multiplier. What if I write just this, y minus y hat transpose y minus y hat? What will we get? So if we had x transpose times x, well, this was equal to xk squared. Right, so from the first vector it takes one xk, from the second vector it takes second xk, second xk, so we get a square. Same will go on here. So from the first vector it will take the error, the difference between the data point and our prediction, and we'll multiply it with the prediction of the same experiment, and it will sum over the second experiment, third experiment, and so on. So next time we will finish this, and now I promise we will plug in this y hat is equal to x times p. Yeah, that's what we already established, and what we will end up with is that p will be equal to some matrix inverted and multiplied by another matrix. So if you are impatient, it should already. Oops, sorry. I can tell you this will. Sorry. One step back. Yeah. It will look something like this. There will be one matrix, another and another vector. You might already try and use this in your exercises. We will derive it next time. Any questions? No. If you want, you can refresh like your knowledge about how do we do the transposes. So how, if we have a matrix A times matrix B and we transpose them, how will the transpose of the product look like? If you don't know this, it's fine. We will go through it next time. B transpose, A transpose, yes. Okay, if everybody is nodding, then I'm looking forward for the next lecture. Dobre, snáď. No.